Hey guys, let's talk about the rational root theorem. So we started to talk about this in class the other day. We didn't get a chance to finish. But what the rational root theorem says is if we have a polynomial and we would like to find its roots, its zeros, its solutions, then if it's something that we can't really factor all that easily, that there's a way that we can come up with a list of potential roots or potential zeros, and that is using the rational root theorem. So the rational root theorem says that if we have a polynomial and we call the leading coefficient p, we call the constant p, so constant we call p, and the leading coefficient we call q. All right, I'm not sure why we call them p or q, but that's what everybody does. So we have p is, in this case, 1 and q is 3. You can ignore the signs, it's not going to really make a difference. That all possible solutions or all possible roots come in the form p over q, where p is the set of factors, or the, so p, we're going to look for the factors of the constant term. And we're going to look at q as the factors of the leading coefficient. All right? So all possible roots come in the form of p over q, where p would be the elements of the set of things that go into 1, and q is the set of things that go into 3. Now, this is lovely because 3 is a prime, 1 is neither prime nor composite, but it doesn't really have any other factors besides 1. So let's make a list of all the things that go into 1. Well, that would just be positive or negative 1. And then the list of things that go into 3 would be plus or minus 1 and plus or minus 3. Usually you put a single plus or minus out here instead of writing it in front of every single one of them, but if you feel like writing it in front of everyone, go ahead. All right, so then if we were to come up with the set of all possible roots, we have to make every combination of these, with this being in the numerator and this being in the denominator. All right, so possible roots for this. All right, so first I'm going to take, well, actually, I'm just going to put plus or minus out front again, but I could do the 1 divided by the 1, so that's going to give me positive or negative 1 over positive negative or negative 1, so that's just 1. And then I'm going to do the same thing here, positive or negative 1 over positive or negative 3, so we get plus or minus 1/3. This set right here, if none of these are roots or solutions to this polynomial, then there are no rational roots. All right, so this is the complete list of possible rational roots. There are no others. You can't say, well, maybe it's a 7 or maybe it's a 9. No, if it's not in this list, it is not a possible rational root. All right. So let's go on and do a couple others of these because I just want you to see how we come up with that list. So again, here, that we're going to call p. Here, q is our leading coefficient. It's 1. So to come up with the set of things that we would call factors of that, it would be plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Those are all the factors of 10. And then for q, I would just say, well, since it's 1, the only factor of that is plus or minus 1. So the possible roots of this polynomial would be, if I take each one of these and divide it by each one of the factors of q, again, this is really nice because the only thing that goes into 1 is 1. So this is going to be 1 divided by 1, which is 1. 2 divided by 1, which is 2, 5 divided by 1, which is 5, 10 divided by 1, which is 10, and again, we need the plus or minus out front. So these are all the possible roots, rational roots of this polynomial. Now, that doesn't mean that there aren't irrational ones or imaginary ones, But this gives us all possible rational roots. Sorry, I should write that in there. Possible rational roots. All right, again, I'll put it up here. Possible rational roots. Okay, let's take a look at number 4. So again, P is 8. So when I write that list, it's going to be plus or minus 1, 2, 4, and 8. Those are all the factors of 8. And then Q is 5. So that list that I'm going to come up with is plus or minus 1 and plus or minus 5. So when I'm trying to come up with possible rational roots, I have to take every one of these and divide it by every one of these. So again, it's good to be organized about this so you don't miss any. So first I'm going to take each one of them and divide it by 1, and then I'll go through and I'll do it again, each one of them divided by 5. So 1 divided by 1 is 1, 2 divided by 1 is 2, 4 divided by 1 is 4, 8 divided by 1 is 8. Then let me do it again, but this time do it over 5. So 1 over 5 is 1/5, 2 over 5 is 2/5, 4 over 5 is 4/5, and 8 over 5 is 8/5. Now we put the plus or minus in front, and this is all possible rational roots. All right. The more factors that these have, the more possible roots that you're going to get. The less factors, the less possible rational roots. So for example, right here, 27 has very few factors and 1 only has positive or negative 1. So we're going to get fewer here than we would say here. 64 has a ton of factors. In fact, if we list all of them, we get plus or minus 1, 2, 4, 8. Then also 16, and let's see, I've got to have a 64 in here, 2 times, 32, 4 times 16, and 8 times 8. Yeah, so all of these possible roots would work for that. All right, but again, we'll find less for things like down here, 2 and 7 are both prime, so each of these only has one pair of factors, 1 times 7 or 2 times 1. We're going to have less possible solutions or less possible roots. All right, now you might be saying, Mrs. Taylor, great, I can find the possible rational roots, but what do I do with them? All right, so let's take a look at problem number 9. Again, 9's going to be nice and easy because there aren't many possible rational roots or possible rational zeros here because our leading coefficient's 1. So I'm only going to have one thing in the list of factors of Q, plus or minus 1, and 3 is a prime. So for P, it's plus or minus 1 and plus or minus 3. So the possible rational roots, let me go up here because I'm writing a little too big for the amount of space I have. So possible rational roots, again, zeros is another word, would be plus or minus 1 and plus or minus 3. That's it, because I'm dividing by 1. Okay, so here's what we do. We use synthetic division. All right, I might not know how to factor that, but I know that if I have a list of zeros or potential zeros, that I can find if it factors by using synthetic division. Now, if you had a graphing calculator, this would be a lot faster, but since most of you don't, we're going to do this by hand the old school way. So my suggestion to you is start with the smaller ones and work your way up. And if there are fractions in the list, like there are here, I would wait until the very end to do them. All right, so always start with the integer values first and then move to fractions. But again, I would start with the smaller numbers and move up the list. All right, so let's try positive 1. All right, so I'm going to put 1 here, and then I'm going to write all the coefficients. So this is 1, 1, negative 5, 3. I'm going to bring down the 1. 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2. Negative 5 plus 2 is negative 3. 1 times negative 3 is negative 3. 3 plus negative 3 is 0. that means it goes in evenly, right? So positive 1 is a 0 or a root of this polynomial. So again, we could not factor it. It looks like maybe it's grouping, but when I try and group them together, I don't end up with the same like factor there in the end. So no grouping, which means we have no idea how to factor it. But just from this very short list, I was able to find that 1 is a root of that. Now, you might say, well, should I keep going? Should I try like 3 or -1 or something like that? My suggestion to you, as soon as you get down here to 3 terms right here, stop, because we have much better strategies for finding solutions than using the rational root theorem. So I'm going to rewrite this. And what I've just found is that this polynomial factors into, right? Remember, if 1 is a solution, then x minus 1 is a factor. And then this is the other factor. And again, if you remember how we rewrote this, this is the constant term, the linear term, and this x squared term. So this goes to x squared plus 2x minus 3. Now I can just factor that. This is an easy general trinomial, so I'm going to have x minus 1, and then this is going to factor into an x and an x. I'm looking for two things that multiply to 3 that subtract to 2, and the larger one's going to be positive, so that means we've got a plus 3 and a minus 1. All right, so all of the rational zeros, well, again, the zeros come from setting this factored form equal to 0. So each of these 3 things should be set to 0. So x minus 1 equals 0, which gives me a solution of x equals 1. X plus 3 equals 0, which gives me a solution of x equals -3. And x minus 1 equals 0, which gives me a solution of x equals 1. I already wrote it down, so either I can write it a second time or I can say that this is a double root. All right. Hopefully that's good. So maybe just as you're doing this sheet, you should take a minute first to write down all possible zeros and then go through and start trying. But I'm going to skip this one because, again, there aren't many possibilities. Again, 11 is a prime, and this is a 1 right here, so we're not going to have that many possibilities. So let's move on to the next page, and let's try problem number 12. All right, again, 5 and 5 are both prime, but at least we're going to get some values in here that end up as fractional, so I want you to see that. All right, so if I think of all possible roots, again, P, the list is plus or minus 1 and 5. Q, the list is plus or minus 1 and 5. So if I go through and I do this in a very organized way, the possible rational roots, I'll call that PRR, so I don't have to keep writing it out. That would be 1 over 1, which is 1, 5 over 1, which is 5, and then 1 over 5, which is 1/5, and 5 over 5, which is 1. I've already written that in the list, so I don't need to write it again. All right, so if you end up with a way to reduce, and it reduces to something that's already in the list, don't write it again. All right, I'll put the plus or minus 1, the plus or minus in front of that. And again, my suggestion to you is we now have 6 possible roots. I would start with the smallest one. So let's go with 1 again. I'm not looking at my answer key as I do this, so it might not be right, so I might have to erase. But again, that's just what happens. All right, so we're going to put 5, 29, 19, -5. So let's try that. I suspect this is not going to work. There's way too many positives at first. So it's going to be 5, 5, 29 and 5 is 34. 34 times 1 is 34. 19 and 34 is 53. 53 times 1, no, that's not going to work. If I put 53 here, I do not get 0. All right, so 1 is not the solution. So let's show that we tried it and it didn't work. Now let's try -1. Again, either do this on scrap paper or, you know, just maybe try it on scrap paper and transfer it here. But you definitely don't want to end up doing all of these on here. I'm just doing it so that we stay on the same page here. So let me bring down the 5. Negative 1 times 5 is negative 5. Then we get positive 24. Negative 1 times positive 24 is negative 24. 19 minus 24 is negative 5. Negative 1 times negative 5 is positive 5. Negative 5 and positive 5 is 0. All right, so I just found one of the zeros. So that means I'm going to rewrite this now as f of x equals, if negative 1 is a 0, then x plus 1 is a factor. And then my other factor is 5x squared plus 24x minus 5. This is a harder general trinomial, so I'm looking for two things that multiply to 25 that subtract to 24. Hopefully that's an easy one for you. It should be 25 and 1. So let's try factoring that then. So I'm going to get 5x squared, and I'll have a minus 5 down here. And the 24 I'm going to write as minus x plus 25x. All right, I'm going to do grouping. So out of these first two, I'm going to pull out an x. So that leaves me with 5x minus 1. And out of here, I'm going to pull out a 5. And that's going to leave me 5x minus 1. When I pull out the 5x minus 1s, I'm left with x plus 5. So my complete factorization of this, again, this x plus 1 is sitting here patiently waiting. So my complete factorization is x plus 1, 5x minus 1, and x plus 5. So we would say that all zeros of this are x equals negative 1, x equals positive 1/5, and x equals negative 5. All right, and again, the difference between these and the synthetic division that we've been doing before is not the synthetic division, but you were always given a factor to divide into it. So now we're coming up with our own list of factors, our own potential zeros, and we're doing the division. So this puts us a little bit in the advantage because we're not dependent upon the workbook or somebody else to tell us what values to try. All right, so I'm going to ask you to do some of these, and then I would like you to submit them to me. All right, bye.